Hello, everybody, and welcome to another wonderful day of chemistry. So today we're going to be looking at how solubilities of compounds can actually start interfacing with the pH of a system. So we've already seen little bits of this because it turns out a lot of our solids are going to be bound to very pH sensitive molecules. Specifically, the ions that are really of interest here are going to be hydroxides and oxides. However, you can see this most easily with hydroxide compounds. So one of the great examples is magnesium hydroxide, which you may know as milk of magnesia. So it mostly acts as an antacid. And how it acts as an antacid is that milk of magnesia is magnesium hydroxide. So if you ever open up a bottle of milk of magnesia, you're going to notice that it's a white solid suspended in water. So there's always some solid and there's always some dissolved constituent. Well, it turns out that dissolved constituent contains hydroxide. And so what ends up happening here is that as the system releases hydroxide, it will end up essentially increasing the pH of the system, making it more basic, counteracting any excess acid in your stomach. So one of the things that we can do is by determining the amount of hydroxide that's released into this solution, we can figure out, well, what the pH of milk of magnesia is. So it is worth noting that you're going to maintain this pH pretty much as long as you have solid magnesium hydroxide present, as it will maintain a nice ambient level of hydroxide. So let's go ahead and look at the solubility by looking at an ice table. So again, if I'm dissolving magnesium hydroxide, one of the things we're going to notice is we should have no initial magnesium or hydroxide. So any of these ions will essentially come from the dissolving of the magnesium hydroxide. So we can thus predict the equilibrium concentration based on the solubility of the substance. So this will give us that traditional 4x cubed format for the concentrations. And thus by solving for x, we can find the solubility of the system. And so this gives us a solubility of about 1 × 10⁻⁴, or about 0.1 millimolar. However, it turns out this time we're less interested in the solubility, and we're going to be more interested in this x value component, because this gives me the hydroxide concentration at equilibrium. So at equilibrium, the hydroxide concentration should be twice the value of x. So in this case, about 2 × 10⁻⁴. Well, we can use this to go ahead and find the pOH of the system by taking the negative log. So it turns out this gives us a pOH of about 3.5, which we can then turn to a pH of about 10.4. So this is actually kind of a cool feature. Just by using the solubility of a compound, no real acid-base reactions, we found the pH of a solid when placed in water. Now, however, one of the things that is worth noting is that because we're releasing a base, it means that this compound will react with any number of acids and bases in solution. So one of the cool things you can do is say what would happen to the pH, what would happen to the solubility of this magnesium hydroxide if I put it in a buffered solution. So one of the cool features about buffer solutions is they tend to keep the pH no matter how much or how little hydroxide is introduced to the system. Because if I keep adding hydroxide to a buffer, the pH shifts a little, but it pretty much stays relatively constant. So let's go ahead and try and apply this to an ice table solubility system. So what would the solubility of this magnesium hydroxide be if I put it in a pH 10 buffer? So it is worth noting on its own, magnesium hydroxide does tend to produce about a pH 10 solution. Well, so the first thing we're going to need to do is find out what the hydroxide concentration is at a pH of 10. So this gives us a pOH of 4, and then we can turn this into a hydroxide concentration of 10⁻⁴. So let's go ahead and put that in to our buffer system. And so here, there really will be no change in the concentration because the buffer will just pretty much nom up all the extra hydroxide. And so the only concentration here that's really going to be changing is the magnesium. And this will give us the solubility of the system, because any magnesium produced is a magnesium hydroxide consumed. So doing this, we can go ahead and then plug into our KSP value, which will just be the solubility times the hydroxide concentration squared. So this gives us S times 10 to the negative 8. Then solving for S, we find that the solubility will be about 5.6 times 10 to the negative 4th. So it is worth noting that what we saw was a slight increase of the solubility of the system. And by that, I mean it got 5 times as big. And the reason why is because essentially we're keeping that hydroxide concentration relatively fixed, which is going to help try and drive the system forward, as the amount being produced matters a little bit less here. Now, what would happen if I decrease this hydroxide concentration a little bit more? So on its own, the concentration is 10.4. Then we went to a pH of 10, so went slightly lower. Now let's go down and figure out what the solubility, if I drove the concentration all the way down to a pH of 7 be. So first thing we're going to need to do is find the pOH, so 7. And now this gives us a hydroxide concentration of 10 to the negative 7, as opposed to 10 to the negative 4 in the last problem. So that hydroxide concentration is 1,000 times smaller just by moving it 3 pH units. Now we can do a similar ice table, fixing the hydroxide concentration at 10 to the negative 7th, and try and solve for the solubility. So same thing as last time, but now that hydroxide component is going to play a much bigger role, because instead of 10 to the negative 4th squared, it's 10 to the negative 7 squared, which means the solubility is going to be the KSP times 10 to the 14th. So this gives us a concentration of 560 molar. Well, turns out that what we did is we made that system essentially highly soluble. So anytime you see a solubility much above 10, this will start running into problems that we'll talk about next time. But really what we're seeing is anytime you have a solubility more than 10 molar, this is a way of saying the system is almost infinitely soluble. So as long as you keep the pH at 7, this system will keep dissolving until all of our basic rules for how these tables work kind of break down. But the big illustration here is that by changing the pH of our system, we can really end up changing the behavior of a lot of our solids. So if I've got something that has hydroxide, if I go ahead and acidify the system, decrease the amount of hydroxide, I can make any of these basic solids highly soluble. By increasing the hydroxide, I can prevent them from breaking apart at all. So next time, we're going to focus a little bit more on how these solubility tables can break down, and specifically why we're never going to quite get to a solubility of 560. Until then, take care.